So I will be the chair of this first session, and I think we have already online Professor Jurgen Kurths. Can you hear me? Jurgen?
Yeah, I can hear you.
Okay, so we will start if you don't mind. Yeah, are you ready? So Professor Jurgen Kurths is a physicist and mathematician in Germany. He's very famous, so you know he has hundreds of publications, several fundamental books in the area where he is expert. So nonlinear science, chaos, with many applications. And as you can see today, he will talk also about some on networks, but climate meets networks, so networks and also some application to an important relevant field. So thank you very much, Jurgen, to be with us. So you have 40 minutes, I think, and then there is time for questions. Please go ahead.
Yeah, thank you very much, Jose, for the kind invitation. And I really would like to be with you, but you know, this COVID is a bit strange, and I hope it will work also this way. I will talk today about the use of complex networks in, let me say, general Earth science. And the question, the general, is then, are modern concepts of network science useful for Earth sciences? Some time ago, it was not so clear whether all this is part of physics, but now we know officially also, after the Nobel Prize last year, that complexity science as well as climate are really part of physics, which is important for many of us. Then I will talk about some recent challenges of climate change, and then come to a special kind of networks, what we call climate networks. And especially I will demonstrate how it works for extreme climate events. So let me start with the three big guys, Klaus Hasselmann, Giorgio Parisi, Syukuro Manabe, who got the Nobel Prize last year for describing complex physical systems, and especially for their pioneering mathematical model of Earth's climate and increasing levels, and finding that increasing levels of carbon dioxide in Earth's atmosphere would raise global temperature. So a really pioneering work, but the beginning of all this, that physics come into the climate in a strong sense, was by Richardson, Louis Fry Richardson, who published already in 1922 a book on weather prediction by numerical process. And numerical process, he means physical equation, Navier-Stokes equation, as a really physics-based forecast. But this was too early. He had no computers. We had to wait another 3 decades till Jon von Neumann came with his genius colleagues, and they really made it doable. That means they really calculated weather forecast by using of computers based on physics, physical equations. But despite all these processes and despite all these successes, basic problems on understanding fundamental mechanisms and processes were really and are open in some sense. And here the pioneering contributions, especially of Hasselmann and Manabe, sets in. Hasselmann was the first to describe the climate system as a random system. That means he found an analog to the Brownian motion and described then the whole dynamics in form of a Fokker-Planck equation, where you have propagation term and diffusion term. They all depend on time here and also on the climate state. And with this approach, he was able to solve a huge problem that you always had some, so what we call now a red component in time series, in the power spectra of time series. He really could explain this, that they can be modeled as an autoregressive process of first order or something, also some Markov-like behavior. And with this, he found also a new kind of limit of predictability on a rather substantial and realistic model. This was really a basic contribution. Another, only to give a few aspects of their work, was a coupled ocean climate model by Manabe, developed by Manabe in 1980. And with this, he studied the influence of CO2. First, he took the CO2 as it was that time and considered then the ice near the poles. And he found then that this is almost constant in the Antarctica, but you have a seasonal effect in Arctic. But now then he mimics the following, that we have an increase due to human influences of 4 times CO2 contents in the atmosphere. And then you see, he found, only by numerical analysis, he found a strong change. First, the ice range is much less in Antarctica, and the seasonal effect in Arctica is much stronger. In summer is almost no ice. And we know now from modern observations, this is now 40 years ago, that this comes closer and closer to his prediction that we have a stronger seasonal effect in the Arctic, and in summer it becomes really thinner and less, and probably it really will vanish in much during summertime rather soon. And these were really 2 predictions based on only modeling and thinking, and of course computers, and this was confirmed by data later. This is really great work, and therefore many people are happy that, including me, that they got the Nobel Prize. But we have also recent challenges. You all know about all these extreme events, wildfires, we have heat waves, much stronger and more often happen heat waves also in Europe. And we have snowfall in America, where usually is only a little snow. And this is very typical these days. And one of the most important dangers for the impact of climate change is sea level rise, the rise of the sea level. And this is not homogeneous, it depends on the mass distribution of the Earth, but many huge cities are very close to sea or oceans where we expect a rather strong sea level rise. One famous example is here in Indonesia, where we have Jakarta capital, but we have already floods every year, and it was decided to shift Jakarta to a new city, Nusantara, to another island of Indonesia, already in 24, I think. This will be finished. But there are, of course, is also Bangladesh is very much danger, but also Eastern China, excuse me, Western China, no, Eastern China, Eastern United States, where all these big cities are. We have a big change, and you can imagine if this water will rise, then we will have a much, much stronger migration of people as we have it these days. And this is really a huge point. And one kind of description is via so-called tipping points. Tipping points are regions, sub-regions on Earth where we expect that there is some danger of a qualitative change. That means if there will be some further, maybe little changes, it's not so clear how far we are, then we will have strong changes, really qualitative change. For instance, it was told very recently that the glaciers in Himalaya are melting much faster than expected. For us, very important is this Arctic ice melting in both poles, also in Antarctica. And then we have, which is very important also for Europe, this Atlantic thermohaline circulation, that the warm water is coming from the Gulf of Mexico and so north to northern Europe, cooling down, and then the cool one is going southward. It's like a conveyor belt. And if this becomes slower or stops even, then we will have a very strong change of our climate. And these are these tipping points. And the question is then, what is the interaction among these tipping points? And especially, is there such a domino-like effect that if we have one tipping, then all the others will tip, or is this a bit more isolated? We have made recently a network like these tipping points can be considered as a network. And then the question is to describe the dynamics of each of these tipping points as well as the interactions. And these are very different processes. One is more vegetation in Amazon, the other is more ice dynamics in the poles. You can imagine it's not so easy to find an appropriate description. We made a rather basic modeling with some paradigmatic models and studied only the interaction of 4 of these possible tipping points. And we found this especially Greenland ice melting has very strong effect on the Atlantic Ocean, on this thermohaline circulation, but also going down to the Antarctica and have then also strong effect on the sea level rise. Whereas the Amazon is a bit more isolated. It will not include a tipping of many others as far as we know. And these are open questions, ongoing research with a lot of uncertainties. The data are not known enough, and also the mechanisms. The description is in the beginning. But let me now go, this was more model-based, now go more to data-based climate networks. I would start with a short story. I met Klaus Hasselmann when we started this way of considering the climate via complex networks in 2011. And he listened carefully as a board member of our scientific advisory board, listened carefully, asked a lot of very hard questions. And then after thinking a while, he told me, you should go ahead this way. It has much potential. And this was really a strong encouragement for me. He was famous already 10 years ago. So this is work with several people. These are here my former PhD students and my group in Potsdam. And these are collaborators all over the world, which are especially experts in climate. You need this. So System Earth. System Earth, especially the atmosphere, is of course not a typical kind of network as we have in social systems. This is more a flown system and a flow network, also the ocean. That means we have to consider it a bit different. And the first question is then to construct a network from data, from such continuous dynamic system in order to better understand structure versus functionality. One can state that this is some kind of backbone, but one can also interpret this as some kind of discretization. How to identify such connections, such a network in a continuous dynamic system. But discretization not in the classic manner. It's really different, and it goes as follows. Consider here is the Earth. All these dots are the observation sites, and these are considered as nodes. And then we have measures on each observations, on each of these observation sites. It could be temperature, could be precipitation, wind, humidity, etc. And then we compare the different time series from the different observation sites for similarity, or better saying, for causality. Correlation is often not enough because you have substantial nonlinear interaction. Therefore, you really have to look for correlations, for causality. And if this causality is really significant, then we make a connection between, in this case, node K and I, and construct the adjacency matrix this way, and can then apply all these nice network measures. This way is very convenient to infer long-range connections. They are called teleconnections. And here the strongest are shown from a temperature-driven climate network, which has more than 100,000 edges. And you see this is mostly along the equator, along the oceans, the most important long-range interactions. But there are also other ones. I will come to this. And this is rather the first result, if you wish, which is an important input for climatologists for understanding a lot of dynamics, how the climate happens. But we have then used this to solve a special question. The question was then how is the ENSO, El Nino dynamics from the Pacific influencing the Indian monsoon? And we used then our network approach and found then that there are several pathways going rather north, a bit more south, and this was the most south one we found. And then we looked what is the most probable, what has the strongest weight, and this was very clearly this connection via the Indonesian archipelago. It goes in the atmosphere this way and then this way. And this already was interesting enough, was not clear in climatology. Quantitatively, there were hypotheses, but we have shown it really quantitatively and could publish them in a rather good journal, this finding. But now let me go to a bit different approach. These are extreme events. And I follow a bit here the motto of Richard Feynman, another famous physicist. Test of science is its ability to predict. Let's see whether we can do, because the problem with the state-of-the-art approach for forecasting are the global circulation models. These are continuations of Richardson's approach, and they are working very well for weather forecast, but the main problem is that the prediction horizon is maximum 2 weeks. Also up to 10 days is fine, then it becomes really worse and worse. And several extreme events are not predictable at all. Therefore, the question is how to go beyond the 2 weeks up to seasonal, sub-seasonal, and can complex network approach help? So first, we developed a special technique. You know, I work a lot on synchronization. Therefore, here we also came by in some way via a synchronization approach, which we call event synchronization. What does it mean? If we have precipitation at two different sites, A and B, we consider the strongest one, in this case, the 10% strongest one, and consider when is the maximum. And the crucial question is now whether these strong events happens almost at the same time. And this happens here, here, and here. You cannot expect that it's exactly at the same time, because all these systems, these circulation patterns need some time to go from A to B. Therefore, we considered windows of a few days plus minus 3 days. If it's a larger area, also plus minus 7 days. And if this happens, that they are in such a window at almost the same time, and this happens not only one, but significantly often, then we argue this they are connected. They happen in a synchronized manner, and we make them, as here we have these two observation sites, here, and here, observations, then we make this event synchronization analysis, and if this is significant, then we make again a 1 between these two areas, I and J, and then we can go ahead with network analysis. That's the idea. So now I will show you some application of this simple idea, and will also come to a crucial technical point. We looked for strong rainfall events, especially for long-range events, and from a global perspective. And here we have satellite data, which are very good because they cover all We have not to interpolate or to do some other things, but they are not too long. This TRIM satellite started in 98, but it's not too bad. It has a very good 10 resolution. That means we have more than 500,000 grid cells, 500,000 nodes, and we consider now the 10 up to 1% strongest events. And that means to identify these interrelations, this connectivity, the adjacency matrix, we have to make about 10 to 11 comparisons. This is not a big problem these days with our computers. The problem is another one. This is a so-called multiple comparison or multiple testing problem. And this is a real problem because we take the data from each node and compare with all the other nodes. Take the data again and again and again. This is multiple testing. And due to this multiple testing, this is a classic result in statistics, you get artifacts. That means some interactions look significant, although they are not. And therefore, one makes some corrections. There are, of course, classic corrections, but they are too conservative. If you apply them, then nothing remains. That means no interrelations. This cannot be true. And it took us in this work most time to develop a technique to identify the really significant interactions. And for this, we did not consider only the pairwise connection, but in some sense, the pathway. Also, we looked for coherent spatial patterns or significant bundles, which makes much more sense because these patterns cannot jump from A to B. They have to go a pathway. And this is also for longer distances. And this is in some sense a general conditional causality measure, which we introduced and which really works well. And we could even publish this in Nature. And this was the first paper in Nature at all on climate networks 2 years ago. And this is the result. If you consider, as in this case, this is the red dot is northern India and Himalaya. And we considered strong rainfall interaction with all the other nodes available. And this is in this stripe plus minus 50 degrees. This is a cover of the satellite. And if we include all interaction without correction, then it looks that almost all is connected with this area. This is too much. Then we made this correction and you see already is much less. And the shaded areas have also to be removed because here this is not significant enough. That means we come now really to some sparse adjacency matrix which describes the connectivity. And then we are looking how can we describe all these connectivities? This is a huge number. First we looked for scaling. That means we considered now not only this Himalaya, but all nodes as a possible origin and calculated then the probability density function of the connectivity in dependence on the distance to the original node. And this is a double logarithmic plot. And you see here is a linear behavior becoming less, which is expected, that you have less connectivity as more far you go from the initial node. But then you have a turning point and you have an increase again. Not so strong, not coming to the big numbers, but substantial and significant increase. Then we thought, this is about 2,500 kilometers. What could be the origin? And it is then rather clear after some thinking that this is here expresses the regional weather systems, mostly described by thermodynamics, whereas here we have the teleconnection, that I showed you before from another perspective, the long-range connections, and they are mainly due to the circulation dynamics, large-scale circulation dynamics, and Rossby waves are a very important piece of this. And this was the first, we found such double scaling, if you wish, and we could really distinguish both kinds of interactions. And this could be also a very interesting point to identify teleconnections. This is a hot topic in climatology. What is a teleconnection, what is not? And probably due to this change in the scaling behavior, we have now a very good cutting point to distinguish these two classes. But one could go ahead also. This was a global picture. One could also see then what are typical evolving patterns. And we considered then evolving patterns, say from here eastwards, and found then a pattern which was known in some sense from the Rossby waves, much higher, the so-called Silk Road pattern. And this has to do, of course, with the Silk Road because it goes to Eastern Asia. And this means, this was really a new result, that these Rossby waves, this large-scale pattern in about 100 kilometers or so high, that they influence strongly also the strong rainfall events. This was really unclear, but this opens probably a door for further, for new ways of prediction of extreme rainfall events. Now let me go, have more time to two special examples. And one is the Indian monsoon. And you know, especially the Indian summer monsoon. And Indian summer monsoon is really so crucial for the whole subcontinent. Some people argue even that this is the financial minister of India. If it's too strong, you have floods. This is not good, but much worse is if it's too weak. Then you have really strong problems, especially for agriculture. But a special problem here is to estimate or forecast the onset of this Indian summer monsoon. Why is this so important? Because this has to do when to bring out the seed to the soil. When should the farmers bring out the seed? And you see here is a farmer who brought out it too early. All these seeds died out, no roots could develop, and he lost all. If you bring it too late, then the roots are not developed enough and all is washed out. Also one has to find a good timing for this. And that is our problem, and we try to estimate the onset of the Indian summer monsoon via complex networks. So which data we used again as the TRIM data, the satellite data, but we have there fortunately also a longer data set. This is in the Aphrodite file composed, and this goes back to 1950. So we have then almost 50 years longer time series. It's not so high resolution, but high enough, and it's almost complete real data. One has to interpolate only a bit. Also this is really real data, which is not so typical. And then we use also some typical measures as temperature, pressure, etc. And then we apply not only the climate networks, this is not enough, but we apply 3 steps. First is we identify the most sensitive regions for the onset of climate of Indian summer monsoon via complex network analysis via this event synchronization. This is the first step. Then next, we consider for these 2 regions another typical behavior in nonlinear dynamics, which is called pre-bifurcational enhancement of fluctuations. A terrible word, but very simple meaning. If you have a bifurcation and you give noise to several parameters before the onset of bifurcation, you find that the initial noise variance becomes larger. That means as closer you come to this bifurcation, these fluctuations become amplified, become larger. This is due to the fact that they feel already the bifurcation, that they jump from time to time to the other regime, but will be attracted back to the original regime. That is the reason, and this has been shown for basic bifurcations, but we use this also for India, and then we use also a special situation there that temperature and humidity cross exactly at these from these areas at the onset of Indian summer monsoon. And with this, with a combination of these three steps, we really get a extensive prediction horizon to 40 days before the onset of the Indian summer monsoon, which is much earlier than existing methods. And we have a success rate of 74%. Success rate is estimated in hindcast manner. That means we looked into the past, considered then some past as a future, and made these estimates and came then to this number, which is not bad. So, and to go a bit into the details, what we found, the most sensitive areas is this Eastern Ghats and North Pakistan. This was a bit a surprise because usually Kerala, this area here, is considered as most important for the onset of Indian summer monsoon. This is correct in some sense because summer monsoon from the Arabic Sea and starts here in India and Kerala. But we found out with this event synchronization analysis that most sensitive areas are these ones. Because there one see already large scale, a change of large scale motions. And then coming to this increase of fluctuations. We have, this is here, the growth of variance of fluctuations. This is over time, this is the onset of the Indian summer monsoon. This is for whole India, you see almost nothing. But for North Pakistan, as well as for Eastern Ghats, this is MP and EG, you see really a strong increase of these fluctuations. And this we use then for via interpolation to calculate the onset or estimate the onset of Indian summer monsoon. And finally, we take then also this temperature and humidity, because exactly at this time, temperature from there and from here, they are crossing. And the same with humidity. This has to do with large cyclone and anticyclone motion. So this is fine. This was, we checked this in the past, if you wish, with this hindcast, but the question was, then, is it also successful in real time? And we published this in 2016, early 2016, this result, and could make now several real-time forecasts from 2016 up to 21. And we found that all were successful. All these forecasts, we expect that some will fail, 70% are 70%, but maybe due to climate change is now a bit easier to predict because things are becoming a bit more regular in some sense. But this is not clear. We have not enough data for this. Another problem is that we can estimate the onset quite well, but not yet the intensity, which is also very important because we had strong floods in Kerala, for instance, in 2018. And it would be very important also for mitigation purpose to have an estimate of the intensity. This we are working, and this is going ahead with the corresponding leading Indian institutes to combine our methods with their methods. And we hope that we can really then include this approach in an operational forecast in this Indian system. So let me come to another example, also monsoon, but now in South America, you have there also monsoon systems. This is, of course, in our winter, December, January, February, as their summer. We take the same data and we consider now a special phenomenon. This is extreme rainfall in Bolivia. In these high plateaus in Bolivia, there are from time to time very strong rainfall events, and they have as impact floods and landslides. And landslides, you know, we had it in Germany this last summer, have a lot of economic and social impact. And therefore, a forecast would be important to make some measures. But these events are not predictable at all. And then we thought, can we find some pre-warning from our network approach? And we tried a lot, and then we found the following approach. If we consider very strong rainfall events in the Buenos Aires, Montevideo area, then we followed up. Where is it going? And we found that this goes northwestwards. You see it here. No, you see here, northwestward. And then happening these strong rainfall events here in the high plateaus in Bolivia. And this needs about 2 days to go from here to here. As one could forecast 2 days in advance that there is a big danger for such extreme event. Here is in more detail how it evolves. Okay, this was a finding, a statistical finding and a complex network-based finding. We discussed this with our colleagues from climatology, and they told us, no, this is impossible because rain comes always from north to south, never from south to north. And then we thought a while and came up with a hypothesis that we have, or maybe I show here, that we have cold winds and they are going northwards from the Antarctica, also via Rossby waves, and they are acting as carriers of these low pressure systems and bring them up to Bolivia. We considered this then with real data, forgetting about all network, and found then this hypothesis is really true in more than 60% of all cases and in even 90% during Central Andes. As that means in this case, we have found a new mechanism via the network approach, which also has predictive power. We also have made other applications for tropical cyclones, for extreme rainfall and typhoons and landslides in Japan, for El Nino forecast, which we could really extend it a lot, for the Indian Ocean dipole, a very recent paper, and also we wrote a perspective paper on this approach last year in PNAS. So let me come to an end. I hope I could convince you that climate is a complex system, that both are parts of physics, but this needs really interdisciplinary approaches, and complex networks are a very promising one. And this is, of course, not the only one, but it's for several questions, really we found that we can improve predictions of strong events, of strong climate events. But we hope that we can also use this in operational forecast and maybe also for other kinds of events. But I have to say that there are a lot of open problems. There is the question, is this a potential also for other forecasts, not only rainfall, also for heat waves, for instance, and also for compound events when two extreme events happen almost at the same time and not at the same place, but related places. We will also use then multi-layer networks to include more components in the atmosphere, but also different physical components, and also land use, and will also combine this approach with machine learning methods to make some algorithms faster. We will not replace this completely by machine learning. Some people did it. This is not so successful, but I think combining both disciplines, I see a lot of potential for future, not only in climate, in many other fields also. And I think one could also apply this approach in neuroscience, where we have similar situation with data and similar questions with extreme events, with some diseases. Here are our papers on this topic, and with this, I think my time is over. I would like to stop, and I'm happy to get questions. Thank you very much.
Thank you very much, Jurgen for this timely and fantastic talk. So for those online, there you can ask questions or can set your question in Q&A. Please do it. But meanwhile, I pass to the room and I ask if someone has a question. Is there a question on chat? No? Is there a question in the room? No. No questions? So, Jurgen, apparently it was very clear. Nobody has questions. If there are no questions, so thank you very much. There is a question there is a question, sorry. There is a question on Q&A. Q&A? Okay. There is a question. How scale dependent is the model, is the question.
This is what I showed is data-based. And of course, we used here the full-scale data, this full resolution, but we considered also more rough resolution in order to see whether this scaling and this change of scaling happens also if we have not so fine resolution. And it's really, it's very stable, this kind of scaling for different spatial resolutions.
Thank you very much. So apparently there are no questions. I thank you very much for a fantastic talk. I don't know if you will continue with us, but so there is another question. Another question. Maria Angel Serrano, could you please say a little bit more about how you deal with the causality and the spurious correlations in your research?
Yeah, thank you very much. This is also a crucial point, and this really took us most time and takes us because we are not yet satisfied with the solution. Also first, we considered the classic thing, conditional correlations. This was not enough, not appropriate enough. And this is, of course, to avoid artifacts, to avoid indirect connections as real links. This is the main problem. And then we considered conditional probabilities and so, but they are very hard to estimate. The data are not sufficiently long enough or not stationary enough. We have to make some sliding windows also. And therefore we developed then this search for bundles, also for pathways, which is also in some sense a conditional measure that we can go to C only when we went via B, for instance. Yeah? And this has to be, and then going ahead, not straightforward, but in some sense. And this was then really a good compromise for this kind of data and for to avoid artifacts. We also checked this with a model system. We simulated some flow dynamics with typical flows and then looked for such artifacts. And this method is really rather stable. But this is especially here for rainfall. I think one has to work also. There are open questions if you look, if you go for temperature or pressure, especially if you go for multi-layer systems, then it becomes even worse. And we are working on this, also many others, and I hope and I'm optimistic that will be more progress. But for this purpose, this method really worked very well.
Thank you very much. So I think we will, Sergey, you want a question? That is, please, can you go there? There is one question, Yuri.
Sorry, actually, it is very close to previous question. Your main point of your approach is indication what you call event synchronization, yes? This is the key point of your approach. So, and how can you make it strictly? As I can understand, it's kind of art, but not science. You told about the key point of science is predictability. And your predictability is based on something what is art. Your previous answer was that it's very difficult. Can you make it strictly?
Yeah, this is, I understand. This is also a very good point, because among the open problems is also a more strict mathematical foundation. That is completely correct. But here, let me say again, we have here rainfall, which are more point-like processes. And this is very hard then to identify or to calculate some causality among such point-like processes, point-like in space and time. And therefore we thought, how can we describe well such strong events? And this led us then to this, what we call event synchronization. That means that strong events happen almost at the same time. But this, in some sense, we make it, we transform it into a continuous variable. If you have temperature, pressure also, so you have not to make this step, because these are already continuous time series. And then you can go via the classic measures with all the pitfalls, I know. But here you really, if you have such event-like properties or event-like phenomena, then you have to go a bit different way. But it works, we have checked, but it's not, you are right, not mathematically founded yet. It would be great if someone will do it.
So thank you very much. Let's thank the speaker again. So we have to move to another.